तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Looking at the circuits for arithmetic operations, we first considered adders, which are the most fundamental arithmetic operations, and we also talked about speeding up of adders. One example we took was the carry look ahead. Then we talked about subtractors, and subtraction being a complement addition was taken into account while designing subtractors. And then the most widely used operation in the arithmetic computations is multiplication. So we would like to see multipliers. Of course, there are some different types of multipliers depending on the speed and hardware. It's always the trade-off. More hardware, faster multiplication is possible, but you need to spend more money. If you want to go for a smaller circuit with less hardware, then it will take more time. Basically, the multiplication we understand, as we understand from our paper and pencil method, is to do this shift and add. That is, we take the two operands. One is called the multiplicand, the other is called the multiplier. Each digit of the multiplier, in case of decimal numbers, each digit of the multiplier is multiplied with the multiplicand. You write the result, which we will call partial product. Then we take the second digit of the multiplier and multiply again with the same multiplicand. Write it down from the first product, partial product, but in this, when we do that, we do the shifting, because we have taken the second position of the multiplier. While we write the partial product, we write it with a left shift of one digit position to the left. We continue to do that till we exhaust all the digits of the multiplier. Finally, we add the whole thing to get the final product. This is an algorithm which are used to, which are familiar with in our hand computations. It's called the shift and add algorithm, because we have to add it after shifting it. All the partial products are added together to get the final product, but before doing so, we have to shift each of the partial products to one bit position to the left. Of course, the other method of doing it would be to add the multiplicand multiplier times. That is, if you want to multiply a number n by another number m, I can add m times. Then also I can the product. That's a very slow process. I need to do n additions. So shift and add is by far considered to be much faster and more efficient method of multiplication, which has been used in computers. But as we go for higher and higher speed, whether the shifting has to be done one at a time or all at the same time, because suppose we have only one adder, So we can get one partial product, keep it in a register or keep it in a storage, then get the second partial product, shift it and add it using one adder, then that result I will keep in a storage, then get the second partial product, the third partial product, again add it to the same adder. So with one adder I can, in theory I can accomplish the shift and add algorithm if we have enough storage facility to store the multiplier, multiplicand and the partial results. I can accomplish the whole multiplication in a series of additions one after the other. On the other hand, if I have a series of adders, if all the partial products can be added at the same time, I can get the result much faster because all adders can be added, all the partial products can be added at the same time. So one is a serial operation, one after the other. Partial products are added one at a time till we complete the process of partial product addition. The other is to have all the partial products feeding onto the adders at the same time and then getting the sum in one stroke. Such multipliers are, again, as I said, expensive in terms of hardware but faster. So it's always the conflict between the hardware you want to spend, you want to use, and the time you want to allow. Of course, this is only a simple scheme. There are other schemes in which you can even make these things faster. For example, shift and add can be made slightly faster by some innovation. Similarly, this all parallel, all adders at the same time, that can also be speeded up by some innovation. So speeding up like this carry look ahead from the straight adder to the carry look ahead adder and many other adder schemes which are faster. We can also have multiplier schemes which are faster than the basic things. In basic thing though, there are only three things we can recognize. One is the repeated addition, which is inefficient. We have the shift and add with a set of adders, we repeatedly do it, or a shift and add in which we use several adders working all at the same time. These are the three schemes. Within each one we can speed up using many techniques which we are not going to get into in this course. So what we will do today is to look at a circuit which will do the shift and add all at once. Such an adder, a multiplier is called an array multiplier or a parallel multiplier. Why is it called an array multiplier? Because it reads an array of adders. Array is a lot of elements. So we will see when you look at the circuit diagram, you will know why it is called an array multiplier. Array multiplier. Even array multiplier uses only shift and add algorithm. That means I have to have the numbers put in the proper positions with appropriate shifting in order to get the final result which is correct. Let us take a simple example of two 4-bit numbers. Let us say I want to multiply two numbers A and B, each 4 bits. A3, A2, A1, A0 is my first number. B3, B2, B1, B0 is my second number. I multiply all A's and all B's are either 1 or 0, right? These are binary numbers. So A's and B's can only take values of 0 and 1. So first I have to multiply in a traditional multiplier, paper and pencil multiplier, the shift and add multiplication. What do? You take the first digit of the this is called the multiplicand, this is called multiplier. I think you know that. Multiplicand, multiplier. You take one digit in the decimal system, you take one digit of the multiplier and multiply it with the multiplicand and write the result, which is I call a partial product. Because it's not a complete product, I will call it partial product or intermediate product. Then I take the second position of the digit of the multiplier again multiply it this by the same number and write the partial result, but with a shift. Keep on doing it till I have exhausted all the bits, all the digits of the multiplier, and I have this partial product with proper shifting. Then add column by column. This is how we do it. Now we will do exactly the same way here, except these multiplications are only 1-bit multiplications. Now, so if I multiply this by B0, this will be A3B0, A2B0, A1B0, A0B0. That is the first partial product. First partial product. Second partial product will be obtained by multiplying B1 by multiplying A by again B1, which will be A3B1, A2B1, A1B1, A0B1. Same thing, except that I have to shift it correspond to this position of second bit position of the B1. I need to shift the partial product when I write it down. Third is I am going to multiply the same A3, A2, A1, A0 by B2. I will shift it again, A3, B2, A2, B2, A1, B2, A0, B2, and finally, oh, I am sorry, this should be B3, A3, B3, A2, B3, A1, B3, A0, B3. Add them all up. So this will result in one number, and then I'll just, this is the same as A0, B0, and then this will be added. I'll write the result here. This also can have a carry because this is a one, this is a bit, this is a bit. A0, B0 can be 1 or 0 again. Each partial, each product A0, B0, AN, AI, BJ is a bit 0 or a 1. So it can be either 0 or 1. If both are 1, there will be a carry, right? So I need to put the result and take the carry into this. Add these three, then take the carry here, put the result here, 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 and I may get one more carry finally, because this one bit, the carry of this will go into this, that can itself generate a carry. So how many bits will be there in the product? 1, 2, 3, 4, 5, 6, 7. There can be an 8th bit because there can be a carry here. So we have two 4-bit numbers. The result is can be up to 8 bits, not necessarily 8 bits, can be depending on the numbers. Depending on the magnitude of numbers, the number will be having fewer bits, can have fewer bits. But the maximum number of bits you can have is 8 bits. So we will call this P0, product bit 1, product bit P3, P4, P5, P6, P7. This is P2, P3, P4, P5, P6, P7. So 8 bits, P0 to P7, a maximum of 8 bits can be there. First thing you should know about the multiplication is, when you multiply two numbers, the total number of bits that are resulting is the sum of the number of bits of the two operands. The operand, one operand is called multiplier, the other operand is called multiplicand. The sum total of the number of bits in these two numbers will be the maximum number of bits you can have in the product. In the case of addition, we saw that when you add two numbers with the same number of bits, the result can exceed by 1 bit. Here it is a sum of these two. Now the question is, multiplication is very simple. As I said, I have to add A3 B0, A2 B0, A1 B0, A0 B0 with A3 B1, A2 B1, A1 B1, A0 B0 at the first step. If I have a 4-bit adder with an appropriate shifting of the bit positions, I can carry out this first partial product summation. Then I can use the same 4-bit adder and shift the results appropriately to get the sum of these two. Whatever I got as the sum of this can be added to this. I can repeat it. So I can do repeated additions using the same adder, where I will take one row of the partial product and another row of partial product, first complete the addition, take the result, feed it as the input, take one more row of the partial product, add them, get the result, put it as the input, take the one more row of the partial product and complete the addition. This is the algorithm. Both techniques are shift and add. Shift and add with one multiplier, one adder, not a single bit adder. There should be as many bits. I need to add 4 bits, right? So I need to have a multiplier adder which is a 4-bit adder. On the other hand, I can have at the same time I can add these two numbers. The result of this can flow into this. The result can flow into this. I can have many adders so that I can complete additions as fast as possible. This second version is called the array multiplier because I need an array of adders rather than a single adder. I need an array of adders. This is called array multiplier. That is the most widely used multiplier today. When the cost of these devices as technology has improved, earlier on we used to do this shift and add. In fact, it was so expensive, they used to take one single bit adder, do the first bit addition, and then the second bit addition, then the third bit addition, and complete the one row, go to the next row. That is called bit serial. Bit serial addition is bit by bit serially I will add. Then you go to this second stage where I have a parallel adder with 4 bits or 6 bits or 8 bits or whatever is the number of bits I need to complete my partial product addition of one row to another row. I will take row by row. So row serial. Instead of bit serial, I will have a row serial shift and add algorithm, a shift and add hardware. But now I don't even have to do that because the technology has become so inexpensive. Cost of these things are not at all concerned today. The size is not a concern. Power dissipation is not a concern. We are able to have large ICs, integrated circuits, in which all of these things are packed. So in that case, why do we have to do all this one by one and delay the whole process? If we have it's resources. It's a question of resources. If we have enough resources to commit to my project, I can get it done as fast as possible. Of course, under certain constraints, assuming that all of them can be done parallelly. I cannot commit a lot of resources and do a project fast if my project implementation is a serial, sequential. First step has to be completed before the second step can be taken up. If that is the requirement of my project, I cannot do it even though I have a lot of resources. In this case, we are assuming that all these additions can be carried out at the same time. If I have enough number of adders, I can feed all these partial products or these product terms, which are called product terms. Each individual term I will call a product term. A0, B0, A1, B0, A2, B0, A3, B0. Each one of them is a product term. I will feed all these product terms at the appropriate position with appropriate shifting in my adder array. That's why it's called array multiplier. Array of adders, and get the result as fast as possible. Such an adder is called multiplier is called an array multiplier. But how are you going to get A0, B0? It's an AND gate, When you have two numbers, 0 and 1, multiplied by another number is also 0 and 1. The only case the result will be 1 is when both are 1. All other cases the result is a 0. Is it not the same as the AND operation? I have A and B, AI and BJ. My individual product term AI BJ will give me AI BJ. If both are 0 or one of them is 0, the output is 0. If both are 1, the output is 1. So each of these product terms can be generated using an AND gate. So first resource I need to commit for my multiplier is as many AND gates as there are. How many? I need to generate AI ai and bj for each I is equal to 0 to 3, j is equal to 0 to 3. So 4 times 4, 16 product terms I need to generate. So I need to have 16 AND gates. So my assuming I have 16 AND gates, in which I will appropriately feed A0, A1, A2, A3 and B0, B1, B2, B3 proper combinations, I will get ai, bj, where I can vary from 0 to 3 and j can vary from 0 to 3. So in other words, I can have from A0 to A0, B0 to A3, B3. All the 16 terms are available to me at one stroke. With that assumption, I will go and show you how to do the addition process. This is the circuit for which we will do this. This is the circuit of the array multiplier. I have already assumed that all these product terms are available to you using AND gates. All it needs. So if you want to just show this, in one case you can show this. I didn't want to clutter this drawing with all these AND gates in each of these, so I just put an arrow with this product term. You have to assume that each of these product term is coming from an AND gate, like this. So this AND gate will give you A0, B0, and this A0, B0 does not require any more additions. The last row, the least significant column, this becomes the partial product P0, not this partial product. This the first bit of the product term. First bit of the product term P0 is nothing but the A0, B0. So that is why I said A0, B0 is nothing but P0 here. If we take the second column, I need to add A1, B0 to A0, B0. A0, B0 and A1, B0 have to be added. Okay, A0, B1, A1, B0 and A0, B1. A1, B0, A0, B1 have to be added. These two product terms are available to me. I put it in adder and get the result. This adder needs to be a half adder because I have only two terms, no carry, two inputs, no carry, so I need a half adder. The sum goes to P1, the carry is passed on to the, see the carry from this column has to go to the next column, remember that. When I add the partial products of this column to get the product term correspond to this column, the carry from here should go into the next column. So my carry has to travel to the next bit position horizontally. My carry has to travel to the next bit position horizontally. So this is the carry of this adder. This is the half adder. I will put with a H symbol H for half adder, and this is sum. In the third column, I will have to first add A2, B0 to A1, B2, A1, B1 along with the carry from the previous column, and then to that sum I should add A0, B1. Take it as my P2 term, the product term bit number P2 bit of the product, total product, and if there is any carry resulting from that, I need to go to the next stage. So there may be a carry resulting from here, there may be a carry resulting from here. So since they are doing two additions, two carries can be generated. Each of these carries have to go to the next column. The carry is always one weight higher, bit position wise, one higher hierarchy. So the carry from here to go to here, carry from this has to go into this. So that is why I am having here A1, B1, A2, B0, adding to the carry of the previous. The sum goes into this. To add the complete the complete the product term P2, I need to add A0, B2 further. But the carry has to go to the next bit position. So this is my carry, this is my sum, and with this sum I add A0, B2 to to get the sum, which is my P2, and this carry into this. So the carries have to go into the next positions. Some has to travel vertically, carries have to travel horizontally. Do you understand this? That is all. Now I don't have to keep on explaining all these terms. You take each row, each column, take 2 terms at a time. If there has been a carry from the previous position, put it on the top of it, add it, get a sum. If that is the last addition, take it as the particular bit of the product. If it is not the last addition, go to the next term in the same column. Keep on adding some, in all those columns will be added one after the other, and any carry generated has to be pushed into the next bit position, whatever is the stage. So A0 B1, A2 B0 added to this previous carry gets a sum, and this carry to this sum I add A0 B2 to get the product bit P2. This carry goes into this. I am having A2 B1, A3 B0 into this carry. The carry also taken into account, provides another carry which has to go into the next bit position. A1 B2, this sum, this will give me along with this carry. Make sure that you never have more than 3 inputs to the adder, because you can have 2 inputs, it's called a half adder. 3 inputs, it becomes a full adder. You cannot have more than 3. So this is a half adder, because I have the sum from here and this new term. Sum from here, new term. This is a half adder. This is a half adder. All these are half adders. This has to be a full adder, because I need a carry in, these 2 terms, carry out and sum. A full adder will have a carry in, 2 bits as inputs, carry out, sum as the output. So this is a full adder. So full adder, full adder, full adder. So carry from here is pushed into this next column. A3B1 is the first value in this column, A3B1. You draw it this way, it's convenient. I could have always pushed this full adder here, because this carry is coming a new term. But then if you don't keep that symmetry of the drawing, it is very difficult to understand what is happening. So it's better to map your drawing, the hardware, the circuit or the schematic, exactly the same way as the bits appear in your multiplication. So this multiplication can be taken as a reference for drawing this. That is why otherwise I could have pushed it here, it is not going to harm me, because the carry anyway will be there, the new term will be there, and then I can push it down, then it becomes sort of confusing after some time. And it is asymmetric as something else, and this is also better to look at this way, when it's symmetrical. So this goes here, this carry goes here, so this is a full adder. It pushed to the next stage. So this addition process, the carry will go into this. A3 B2 will be added to this carry, and then this will continue, and then finally this will be the last addition of these 2 terms, that will go into this. So this will be the last adder, where A3 B3 will be put along with the carry from the previous position, and this may generate a carry, because there is a bit here, and a bit here, and a bit here. It's a full adder, so there may be a carry here, so you have to put one extra carry. So this is the sum of the last full adder and carry of the last full adder. So in this notation is H is half adder, F is full adder, S is sum, C is carry. This multiplier is called array multiplier. This is the most elementary form of array multiplier. You can make changes in this. The speeding up is possible. Also, we are not talking about signed numbers. If the numbers are, should the numbers be all unsigned numbers or signed numbers? If the signed numbers are the representative 2's complement, how is it going to handle up? Because when you multiply two numbers, the product, the sum of the product depends on the signs of the individual numbers, right? If one of the numbers is negative, the product is negative. If both the numbers are positive or both the numbers are negative, product is positive, is it not? Product, sign of the product is positive if both numbers have same sign. If the numbers have different signs, then the product will be negative. So all these things will be taken into account. So I am not getting into all those details. So this can be improved further for speeding up, can be improved for handling signed numbers and unsigned numbers. For signed number, this unsigned number, for signed numbers. And I can do it for 8 bits, 16 bits, whatever you want. So in general, now I have used 4 by 4 multiplier. This is called 4 by 4 array multiplier. This is the name. What is the hardware required? 16 AND gates. How many adders totally? 4 times 3, 12 adders, out of which 4 are half adders, 8 are full adders. 4 half adders, 8 full adders, total of 12 adders. So we want to generalize this. If you want to call it m by n, m is the number of bits in the multiplicand and n is the number of bits in the multiplier. First number is called multiplicand, the second number is called multiplier. In this case, b is n is 4 for b, n is the number of bits. For b it is 4, a is also it is 4. So here in this case m is 4, n is 4. But what I mean by m is number of bits of a. Number of bits of b is called n. It's only a notation. You can do it the other way also, or you can use it pq, xy. I'm just to keep the notation straight. So if you want to generalize that, there are m times n and gates. There's a half adder in each row. One half adder in each row. Each row corresponds to the multiplier bit. Each multiplier bit gives rise to a product row. Each multiplier bit gives rise to a partial product row. So half adder, the sum of the half adder is the same as the number of bits in the multiplier, right? So n is the number of half adders. What is the total number of adders? N rows, but each row, since we are going to have only one less adder because of this. First we have taken this into account. One less adder in each row, one less than the number of bits. So there are n bits, there are only n minus 1 adders in each row, but there are m rows. So the total number of adders is m into n minus 1. So out of which, number of, I'm sorry, n is the number of half adders, m is the number of, I use, that is okay as long as That means it is m minus 1. I interchanged here m and n. Sorry about it. So the remaining is full adder. That means total adders is mn minus n minus n. So full adders is mn minus 2n or m into n into m minus 2. Number of, isn't it? Number of full adders is total number of adders minus number of half adders. Why? There is a problem here. This is mn minus 2n plus n become mn minus n. Just generalize this. So you have an idea. So I can do an 8 by 8 multiplier. I can even make a m and n need not be same. Is it not? That is why I have given you as m and n. Otherwise I would have put n and n squared and all that I would have given. So I can have a different number of bits for the multiplier and for the multiplicand. So if you know this type of idea of the products, the number of gates and number of adders, half adders, full adders, you have an estimate of the hardware. The beauty is the whole thing is available as a single chip, not even a 4 by 4, even bigger than that. And as I said, this speeding up, extra circuitry for speeding up. As I said, speeding up always comes at the cost of something else. Remember that. And also signed numbers, two's complement numbers. This is unsigned multiplication. Signed multiplier with speed up, larger number of bits. These things are available today, fortunately, as hardware, ICs. So you can just plug it in and use it. Just take it, plug it in your circuit and use the circuit for a multiplication purpose. Now we are talking about this as an improvement from bit serial. Forget about it. Bit serial is olden days. That is, you take only one bit full adder, give A0, B0, whatever, A0, B0. As for example, you want to take one addition. Let us take this addition, A1, B0, A0, B1. You put A0, B0, A1, B0, A0, B1 into the full adder, get the thing, sum and the carry. You should have some way of storing the carry till the new bits are put in the same full adder, because I have only one full adder, remember? To this full adder I will have to get these two numbers. I should have a way of keeping this carry till the time, adding it at the right time, and also keeping the partial products in storage spaces and all that. It was necessary when adders were expensive. When adders became very cheap, when the integrated circuit technology became so easy to fabricate and so inexpensive. So nobody talks of bit serial multiplier today. But the debate was until recently the debate was between partial product, one partial product at a time. I have one multi-bit adder, not a single bit adder as in the case of bit serial adder, one multi-bit adder which will be repeatedly used for first adding this to this and then adding this to this and adding this to this and adding this to this. That is called, as I said, serial parallel, row serial, right? Row serial. Row serial was until recently being used because of the expensive nature of these array multipliers, because it requires, this is not, see again as I said, in the classroom we can do a 4 by 4, in a textbook you will find 4 by 4, but if you want to do a real job, 4 bits is only 16, 0 to 15 numbers, and out of this if you use signed arithmetic, it is plus or minus 7 if it is case of ordinary sign magnitude representation. If you get a 2's complement, it is minus 8 to plus 7. Such a small range, nobody uses a multiplier. You can do it by mental sum, by tables. So we are talking of here 16-bit multipliers, 32-bit multipliers, 64-bit multipliers. So it's all exponentially it grows, the number of gates and full adders and all that. It becomes cost effective to do this. It will become, because the speed has become such a critical issue today. We are talking of computers which have to work in nanosecond clock cycles. So naturally I need to have a hardware for multiplication which will be very, very fast. The only way to achieve is to have this all of them available at the same time. So commit as much resources as possible to get the job done as quickly as possible. Having said that, is it all that fast? We will have to see, because after all there are adders. Adders suffer from what? Carry propagation. We saw it in adders. Carry propagation is a big issue. Here also there is a carry propagation. This carry has to go here and then trigger this. This sum will go. Of course there is no worry, because until I have P7 I cannot use this product. So let me see how quickly can I get P7. I cannot use the full product until all the bits are in place. Is that right? So even though sum may take more time, once this carry is available here, this will be fired. This sum will go here, carry will go here. I will not worry about this path anymore. I will worry about what happens to this carry. How fast can I get it here? Similarly, how fast can I get this carry here? 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 So number of carries is 1, 2, 3, 4, 5, 6. If I call Tc as the carry time or carry propagation time, and Ts as some propagation time of a full adder, of an adder I will say, I will not worry about full adder or half adder. In fact, for symmetry's sake, I always say have uniformity, don't worry about a few full half adders, and if you are talking about 64 by 64 or something like that, talking of so many adders, a small number of them needs to be a half adder, need not be taken into account. You can all have them all full adders with carry 0. That's not a big issue. So we will not worry about propagation time separately. We will call it Tc is the carry propagation time and Ts is the sum propagation time of an adder, whether it is full adder or half adder. We will assume them to be the same. The speed would then be here. This is available after Tc. This is available Ts. So this is available after Ts. Ts is the sum time. This is available instantly. I am not considering the add time. If you consider add time as an extra time, Ta as the AND gate time. So Ta is common to all. All product terms are available after Ta. So I will not worry about it now. Finally I can add this Ta. Isn't it? Finally I can add my Ta. So I will not put Ta plus and all that. So this is immediately available after Ta. This is Ta plus Ts. This will be Tc plus 1 Ts, 1 Tc, 1 Ts. Oh, Tc plus 2 Ts. This is 2 Tc plus 3 Ts, because 1 Tc, second Tc, Ts, Ts, Ts. This will be 3 Tc plus 3 Ts. This is 4 Tc plus 2 Ts. This is 5 Tc plus 1 Ts, and this is 6 Tc. So this term is available after 6 Tc after the multiplication has started. This term is available 5 Tc plus Ts after the multiplication has started, etc., etc. Usually Tc is more than Ts, because isn't it? First, if you assume that, of course you can always make an adder in which Tc is faster than Ts. So if Tc is greater than Ts, if Tc is greater than Ts, I will not worry about this Tc's because I am only getting it 6 Tc is the largest number of Tc's. So the propagation time is 6 Tc. The add time, total add time is Ta plus 6 Tc, and 6 is only a number for this particular combination. In general it will be n minus 1 plus m minus 1. 1 less for n, 1 less for m. So this will be R Ta plus this is the time at which I will get the final result. It is not called total add time, multiplication time. Is this for this particular case, or in general it is this? If for the other hand you have a circuit which is efficient, because many times if you make a circuit Tc is faster than Ts. Why? Because Tc has to carry on, Ts is only local. Ts is a local phenomena. Some propagation is a local phenomenon, carry propagation is a global phenomenon. It has to go. So because of that, many times you want to optimize the circuit's configuration such that Tc becomes smaller than Ts. If that is the case, what will happen? If Tc is less than Ts, then the propagation time will be Ta plus 3 Tc plus 3 Ts, or in general it is Ta plus n minus 1 Ts plus m minus 1 Tc. Same as this. That is why I wrote both. So this is also important. Ts. Even though this carry would have propagated, I have to wait for this. In 3 Tc, this is available. After this, 3 Tc is common between these two. This 6 Tc, this 3 Tc. But after this time, another 3 Tc time this is available, whereas another 3 Ts time only this is available. Now Ts is larger than Tc. That means this is going to be, P4 is going to be the last, not P6. Earlier we said P7 was the last to arrive. Now because 3 Tc is common between these two, 3 Tc after this is available. P7 is slightly earlier available because Tc is smaller than Ts, whereas 3 Ts is going to take a little more time. So P4 will be the last to arrive. So I will have to take that into account. Again it is n minus 1 formula. So why did I say all this about the speeds? I said I am committing a lot of hardware here. Instead of a row serial addition, I am having an array of instantaneous addition. I hope to achieve instantaneous. Moment the numbers A and B, number A and number B are given, I want a product P, which is A times B. But of course it is limited by hardware, which is AND gates and array of adders, and we have to make sure that this is faster than this. Of course there are techniques to speed it up. As I said, I am not going to discuss those things in this class, but the point is you have to see whether the resources committed are able to get what you want. If in spite of that you are not able to get these speeds that you are going to get, I don't want to use it. See, before committing a lot of resource, you have to make sure that you will get the job done in the time required. If you cannot still meet the deadline, what is the point in committing a lot of resources to that? So I can think of another way of improving. Can I get some more resources and speed it up, or reach a point, no, the technology cannot deliver what I want, so I will go back and do the old way, old-fashioned way, something like that. Okay, with this I will conclude the arithmetic circuits. We talked about adders, half adder, full adder, multi-bit adders, fast adders. Carry look at adders as an example only. There are many other fast techniques which I have not considered in this class. We talked about subtractors, and subtractor being 2's complement adders. We talked about multipliers and different schemes, and then one of them. Just tell you the flavor, just to give you the flavor for multiplication hardware.